Let's start our lecture. Today is the 5th of December. And I want to discuss with you a very important issue related to neutrino oscillations phenomena, that is the coherence of neutrino states, and we shall derive the condition under which the phenomena of mixing and oscillations may appear. So there are inherent limitations for this phenomena to appear due to uncertainties in the production region of neutrinos, and as a result, there is an uncertainty between the length to neutrino species propagate from the source when it was produced to the detector point. And these considerations put an inherent limit for observability of neutrino oscillation phenomena as it is. So it is very important to understand and to analyze a particular experimental neutrino fluxes from different sources. And the title is The Coherence in Neutrino Oscillations. In neutrino oscillations. So, let's suppose a kind of experiment when a neutrino, suppose it is a muon neutrino, is produced in the decay of pi meson with the appearance of muon and muon antineutrino. Yeah? So then, let's a bit like this, and that will be neutrino. Pi plus to muon plus. Then this neutrino propagate and arrive to the detector. And here, if there is a room for neutrino oscillation phenomena, we shall see electrons that will indicate that part of muon neutrinos have been transferred to electron species. So this is an ideal picture. And now let's consider the case and suppose that there is mixing of neutrinos. In the initial point, it means that the muon neutrino appears like neutrino with mass 1 and 2, like some mixture of these two mass states. We consider two neutrino mass states and two flavor states, for simplicity. So with some amplitude, neutrino muon can manifest itself like neutrino 1 with mass 1, and some amplitude B, neutrino 2 with mass 2. So this is the obvious starting point when we suppose that neutrino flavor states are mixtures of mass states. Okay? So, and now if we measure carefully the state of motion of charged particles, then in principle we can chance to understand for which mass states neutrino appears here, in which, depending on the accuracy of measurements from the energy momentum conservation. Yeah? This is the point. So, so in the initial point, T0, the wave function of neutrino is the sum over mass states. Lambda stands for the mass states, 1 or 2. The mixing matrix mu E neutrino of alpha state, and we can write it in the following way: this sum over alpha mixing matrix exponent I so this is in the initial point. So for a later period, we can write that neutrino in some later point t we have the following decomposition over the mass states, accounting to the running, and this is alpha, I should put alpha, please. Yeah, accounting for the mixing. Exponent I vector of momentum x alpha E I t nu alpha. So, hello. So, we have just started discussion of a very important issue related to neutrino oscillation phenomena, and that put really an inherent constraints for the observability of neutrino oscillation phenomena in a real experiment. And the title of this lecture is The Coherence in Neutrino Oscillations. Yeah? So we consider neutrinos that are produced in real process of pion decay to a muon and to a muon neutrino. And after after the neutrino bunch pass a distance to the detector, it might happen that we shall see electrons. It means that at least part of muon neutrinos, initial neutrinos, behave in the detector as an electron neutrinos. Yeah? So it means that the phenomena of mixing and oscillation is present. And initially, in the starting point, neutrinos are produced, let's say, in a muon flavor state, and it is a superposition of two mass states, neutrino 1 and neutrino 2. We consider the two neutrino mass states and two flavor states. So here I just write an expression for the initial neutrinos in initial time t0 as a superposition of mass states. And this is the mixing matrix, and this exponent accounts for the effect of propagation. We consider this as a plane waves. So in a later period t, we just generalize this expression and again write alpha, I just missed. I write the expression for this neutrino state in some distance x and some time t as a superposition of two mass states. Yeah? And and now the question that we would like to examine and find an answer: what is the phase difference between two mass states arriving to the detector? The phase difference. The phase difference of two neutrino species, of two neutrino and we can write that the mass difference, the phase difference, depending on time and distance that travel neutrinos, just from the expression for the evolution of neutrinos in space and time. This is the difference of energies, E1 minus E2 multiplied by time plus, or minus, because this is plus, here is minus, the momentum of the first mass state minus the momentum of the second mass state multiplied by R. Yeah? Oh, okay. Just in our next derivations, we shall use the following reference frame. We just introduce x as a directional propagation of neutrinos. Okay? So, and we should calculate. And then we should examine the uncertainty in the phase differences. So we are interested in the uncertainty. And obviously from our experience of wave phenomena in optics, if this uncertainty in the phase difference of two waves will be big enough, there will be no room for oscillation phenomena. Like in optics, yeah? When we consider light, two lights as waves, yeah? So first we calculate this guy, and then we examine uncertainty. And we shall express the uncertainty with the conditions of a real experiment. This uncertainty will be determined by the difference or uncertainty in the production point of neutrino in the source. This is what we are planning to do today. I just have to. So, of course, we shall start with the energy momentum conservation. So, again, we have pi decay into mu plus neutrino. So, we have the following. And we use the following notations. So, this is for momentum for pi, mu, and neutrino equals to the energy of pi or mu or neutrino and momentum. Pi, mu, and neutrino. And neutrino here stands where the neutrino 1 or neutrino 2 with mass is 1 with mass is 2. So from here we just get the following, that pi minus mu squared equals to mu equals to pi to mu squared. Yeah. So then we can make these calculations. The pi mass squared plus the mu neutrino squared minus pi neutrino equals to the mass of mu squared. And we just use this equation for two neutrino, neutrino 1, neutrino 2, with the mass is 1 and mass is 2. And we have two expressions, two relations, and we expand one from another. Yeah, and we get the following. Here is this two equations, and we get the following, that pi mass squared plus mu neutrino squared minus, but I have written this guy, yeah? So, and the result is that for neutrino equal to neutrino 1, neutrino 2, and somehow sum up with neutrino mass squared first minus neutrino second mass squared minus double for momentum of neutrino multiplied by momentum of pi plus neutrino 1 double momentum of pi neutrino second equals to 0. Yeah? So this is the consequences of the energy momentum conservation for two neutrinos, neutrino 1 and neutrino 2. So now let's simplify this expression and consider the case of non-relativistic pi. Or the pi trace, or non-relativistic pi. So then, this combination that enters twice, we get this is the energy of pi, the energy of neutrino 1 or 2, minus momentum neutrino, momentum pi, and for non-relativistic neutrinos, we can neglect this term, and we get that this is the energy of pi multiplied by the energy of neutrino. Okay? So we suppose here that the momentum of pi is approximately 0. Yeah? Okay, then we get one important consequence from the energy momentum conservation. I put here and just put a number 1. We get that the energy of neutrino 1 minus the energy of neutrino 2 equals to approximately, for relativistic, non-relativistic points, the mass of neutrino 1 minus squared mass of neutrino 2 squared divided by 2 energies of the pi. We just should not forget this expression. Yeah? So this is one ingredient or one contribution to the phase difference. Yeah? Well, then let's calculate the second term that contribute to the phase difference of our neutrinos, of two neutrinos. So the second term in the phase difference. So this term is proportional or expressed as, so I will put a short notation. So momentum of neutrino 1, I will just write P1, and momentum of neutrino 2, I will write P2, like, just to be shorter, yeah? So 1 minus 2, and also we will put like this 1 minus 2, this is modulus, multiplied by x. We agree that propagation is along x direction, yeah? Okay. And also the mass of neutrino 1, we will put like mass 1, and the mass of neutrino 2 will be mass 2, and the same for the energy. Neutrino 1, neutrino 2 equals to energy 1 or 2. Okay. So, from the obvious relations, we can write the following, that the modulus of three-dimensional momentum 1 squared minus the modulus of the three-dimensional momentum 2 squared equals to the energy squared minus energy squared minus m1 squared plus m2 squared. Yeah? So now we can rearrange terms. We can rearrange terms and use this expression for the difference of energies. Yeah? We have here the difference of energies, and we can rewrite it in the following way, that this is energy 1 plus energy 2, mass square difference, m1 squared minus m2 squared, divided by 2 energies of the pion. Yeah? Minus m1 squared plus m2 squared. And then the last step here, mass 1 squared minus mass 2 squared divided by 2 energies of the pion multiplied by the energy difference E1 plus E2 minus twice mass energy of the pion. Okay, and then we can express this particular term we're interested in. And we got right here in this corner. This is the second important relation we have derived. We get that the momentum modulus of momentum neutrino 1 minus modulus of momentum neutrino 2 equals to mass 1 squared minus mass 2 squared divided by 2 energies of the pion multiplied by the energy of first neutrino plus the energy of the second neutrino minus 2 energies of the pion divided by sum of momenta of 2 neutrinos. So this is what we have obtained from the energy momentum conservation. And now we can sum up these expressions and write the final expression for the phase difference of 2 waves when they arrive to the detector. The phase, finally, the phase difference in the detector. The phase difference of 2 waves that correspond to neutrino of the mass 1 and neutrino of the mass 2. This phase difference depends on the distance and on time, and it is energy of the first neutrino minus energy of the second neutrino multiplied by time minus momentum of the first minus momentum of the second multiplied by the distance. And we obtain, using 1 and 2 expressions, the following: m1 squared minus m2 squared divided by 2 energies of the pion plus, again, mass first squared minus mass second squared divided by the sum of energies E1 plus E2 multiplied by time I just add this term minus, I make some recomposition, the same m first minus m second squared divided by the same E1 plus E2. I just edit these terms. Edit and extract these terms. Minus momentum 1 minus momentum 2 multiplied by x. So, and now we can rearrange terms here and get the following. This is m1 squared minus m2 squared divided by the sum of energies E1 plus E2 multiplied by time plus, again, mass 1 squared minus mass 2 squared divided by 2 energies of the pion multiplied in denominator the sum of energies E1, E2. And here we should multiply by the sum of energies 1 plus E2 minus double energy of the pion multiplied by T. So we just add something, then extract the same and rearrange terms. This is like very simple algebra, yeah? And we can continue here. So finally we get, again, the phase difference of two waves equals to, after some very simple calculation, m1 squared minus m2 squared divided by sum of energies of neutrinos, mass states, multiplied by time, plus momentum of the first minus momentum of the second neutrino. Here, momentum 1 plus momentum 2 divided by sum of energies 1 plus E2 multiplied by time minus x. This is the final expression that we would like to analyze now. But before going further here, I would like to make a note, or just make a reminder. I would like to introduce or just recall for you the so-called oscillation length. It's an important length that corresponds to effect of oscillations, yeah? Well, if we have two neutrinos, electron and muon neutrino, so they are superposition of neutrino mass states, yeah? Then if we just introduce mixing and oscillations, we can write that the probability of electron neutrino observed as another flavor neutrino, muon, is sine squared, double mixing angle, multiplied by the sine squared mass square difference divided by 4 energies x. Yeah? And this guy, this particular guy, can be expressed through the oscillation length. This is equal to pi divided by L. L, the oscillation length. The oscillation length. So the oscillation length equals to 4 pi's multiplied by energy divided by mass square difference. The oscillation length. So sometimes we just put the indices, accounting, just recalling that there are two neutrinos with two different masses, M1 and M2. This is an oscillation length. This is that I would like to recall. So this is a reminder, and I would like to fix your attention on the second term here. I would like to examine this term. and just to discuss the physical meaning of this term. So indeed, the second term can be neglected. For the case of relativistic neutrinos, but we agree that neutrinos are always relativistic, yeah? Can be neglected for relativistic neutrinos. We know that the only discussed, not observed yet, non-relativistic neutrinos are neutrinos from the very, very early stage of the universe. Yeah, so they are really. It is predicted that they should be non-relativistic, but nobody nobody measured these neutrinos, observed these neutrinos. So what we can write that the travel distance is related to with the speed with time, and this is exactly P1 plus P2 divided by the sum of energies 1 plus E2. Yeah? And if so, this will be 0. I just probably put some additional remarks here. So we can introduce the well-known factor gamma that is inverse proportional to the square root of 1 minus the speed beta. This is the speed of the particle, the gamma factor, where gamma is the ratio of the energy to the mass. So then we can write that beta squared is the energy squared minus m squared divided by the energy squared. And this is what we have used, the momentum squared divided by the energy squared. Yeah? This is like, this is the speed, yeah? I just recall. Say, well, now, after this, we can, from the relativistic neutrinos, we can write that indeed the phase difference for relativistic neutrinos is approximately equals to the mass square difference, divided by energy of the first plus the energy of the second multiplied by time. That is the final estimation for the phase difference of two waves of two relativistic neutrinos arriving from the source to the detector during time or x. It depends how you just choose this. So, and now we are interested in the uncertainty in the phase difference, because this is a critical value that should be not big. If it will be big enough, there is no room for any oscillations. Yeah? No, any oscillations. Okay, I have to clean once again. So the uncertainty of the phase difference depends on the uncertainty of neutrino energies. And we can write that uncertainty in neutrino energy is proportional to the uncertainty to neutrino momentum, obviously, yeah? Okay, just then we determine the uncertainty in the phase difference as an uncertainty on the following expression that we have obtained, mass square difference divided by 2 energies. Yeah, and here we have to calculate the uncertainty of 1 over momenta. That is equal to 1 divided by squared momentum, uncertainty in momentum, yeah? Now, by the way, the uncertainty in momentum is inverse proportional to the uncertainty of the distance due to the uncertainty Heisenberg principle, yeah? Okay. So, just to sum up all of this, we can write the following, that uncertainty in the phase difference, that again is the uncertainty of this combination, energy, equals to mass square difference divided by 2, uncertainty of the energy in the denominator, multiplied by x, yeah? Equals to the uncertainty, the mass square difference divided by 2, the uncertainty of 1 over momentum, x, equals to mass square difference divided by 2, momentum squared in denominator, uncertainty in momentum, x, equals to mass square difference divided by 2 momentum squared, uncertainty in momentum multiplied by x. This is the final evaluation of the uncertainty in the phase differences, phase difference in 2 neutrino waves, arriving to the detector. And now we can introduce the so-called oscillation length. We can introduce the coherence length, the key value, the coherence length. The coherence length in neutrino oscillations, yeah? For neutrino oscillations. So we introduce that the distance that neutrino fly, just travel from the source to the detector, equals to the coherence length when the difference of phases, phase difference, is rather small. Normally people use less than 1, but this is an angle. I prefer to write here a reference angle, the maximal angle. Obviously, it should be written here much less, yeah? But we will fix this relation when delta phi equal to 1. This is the criteria. We introduce the oscillation length when the difference of the uncertainty in the difference of phases is equal to 1, or 2 pi's, according to my taste. Yeah, Yeah. So we just calculate the difference of phases, uncertainty in difference of phases, and introduce the oscillation coherence length, saying that it will be when this delta phi equal to 2 pi's. Yeah? And from here, we just introduce a criteria. We can write that coherence length equals to 2 momentums divided by uncertainty in momentum, mass square difference, delta phi, when delta phi equals to 2 pi's, it means that 4 pi mass square difference. So this is a definition of the coherence length. And just with this introduced coherence length, we can calculate very practical, very interesting characteristic of neutrino oscillation phenomena. That is the number of oscillation peaks, maxima and minima that can be observed. Like an outcome of these exercises, we can derive the number of maxima and minima in the oscillation pattern. Yeah? So we should compare the oscillation length with the coherent length. So the number of maxima just equals to coherence length. This is a length along which oscillation can appear, and also we divide to the distance between two maximas. Yeah, this oscillation coherence length, oscillation length, and we just put all this that we have in our hands. This is 2 pi divided by mass square difference, delta mass square difference divided by 4 momentum, just it is the ratio of momenta to the uncertainty of momenta when neutrinos are produced. And normally, this value is rather big if you are within this coherent length. If you exceed, if, for example, neutrino travels distance longer than this coherent length, n will be less than 1. It means there will be no oscillation. Yeah? So now we can also discuss a very interesting phenomena and a very interesting point. Related to the constraints on observability of oscillations due to uncertainties in the region where neutrinos are produced. So I would like to supply the very well understood statement that if you measure manage to measure very carefully the energy momentum of pi and muon, from the energy momentum conservation, you can derive or understand in which particular mass state neutrino is produced. Understand, yeah? If the uncertainty in measurements of an energy momentum of pi and muon from an energy momentum conservation, you can say whether muon neutrino have been produced as the neutrino of mass 1 or 2. It depends, this option depends how accurate you can measure. Let's suppose that you can measure enough accurately and you see in which particular mass state muon neutrino appears. Then, obviously, once neutrino appears as the mass state, there is no oscillations. We know, because the mass state is the integral of the motion. Yeah, understand? So when you are sure that muon neutrino is exactly 100% neutrino of mass 1 or 2, there is no oscillations. It will survive forever. Yeah? And I would like to supply this with some formulas, and sometimes it's called as follows: incompatibility of experiment on oscillations to measure, to see oscillations, with an experiment for a double peak. So if you measure very carefully, and if neutrino is produced as neutrino 1 or 2, you will two peaks in the energy of muon, depending on which of neutrino of mass 1 or 2 have been produced. Yeah? And the statement is, it is not possible, I just explained by words, it is not possible to make very accurate measurements and to understand in which particular neutrino mass state appears. There is no oscillations. And this statement sometimes people formulate as the following, that incompatibility of two types of experiments. The first for observation of oscillations, and to see two peaks, maximas in the energy of muon. Because if you will see two, you will see in which you can answer the question in which mass state neutrino appears. But I would like to supply with some formulas. So this is like an outcome of our exercises with the coherence length. Yeah? Incompatibility of two experiments on oscillations and double peak. So, first, several steps in our consideration. First, if we measure if one measures, if to measure the momentus of pi and muon with high accuracy, high enough, then we can determine with high energy, with high accuracy, and we can answer whether neutrino were produced as neutrino of mass 1 or 2, or see two peaks. Yeah? The second, but we know that there is an uncertainty principle in that relates the uncertainty in momentum and the coordinate. It is not less than 1. then if this is very small, it means that this guy is rather high, yeah? And the coherence will be lost, yeah? I would like to illustrate this. These relations between uncertainties in momentum of pi and muon and the determination of momentum of neutrinos is based on kinematical relation between the energies and momentas. Yeah, for neutrino 1 and 2. And from here we can just immediately derive that the arrow in determination. So in order to specify in which particular mass state neutrino appears, we should measure this in the accuracy that can distinguish neutrino of the mass 1 and 2. It means that we have examined the mass square difference. So, from this obvious relation, we can see that the arrow, the uncertainty, arrow indetermination of neutrino mass can be expressed delta m neutrino squared equals to, just from this relation, as we know from the first course, or just even from the school, yeah? How we just calculate this uncertainty, is square root of double energy of neutrino squared multiplied by uncertainty in neutrino energy squared plus double momentum neutrino squared multiplied by the uncertainty of momentum neutrino squared. So, then the critical point. nu1 and nu2 are distinguishable, can be distinguished. Can be distinguished only in the case, only if the uncertainty in measurements of the mass of neutrino, delta m squared, is less than the mass square difference of neutrinos. Obviously, yeah? So you should measure you should measure momentums and then calculate the masses with uncertainty less than the difference of masses, obviously. Yeah? In other case, you will not see in which particular mass state neutrino have been produced. And this is put exactly the limit for simultaneous experiments with oscillations and measurements of double peak. So then, number 5, the 5th point, we can write, we just concentrate on one part of this. We can write that the square root of 2 momentum squared multiplied by the uncertainty of momentum squared should be less than the mass square difference. Okay? This is obviously positive. I just forget this positive guy, and this is the consequence. So, and from here we get that the difference, the uncertainty in momentum is less than the mass square difference divided by 2 momentum. So number 6. We know that the uncertainty in neutrino momentum is inverse proportional to uncertainty to the x, the distance that neutrino travel. Yeah. So the next step, recall the oscillation length of 2 neutrinos, 1, 2, I just put these indices, 2 momentum of neutrinos divided by mass square difference. So now if we sum up all we have derived, number 6, number 5, we arrive to the following result, that uncertainty in the point where neutrinos were produced is bigger than neutrino oscillation length. What does it mean? We just have proven this statement. It's not possible to simultaneously arrange an experiment. Obviously, this without any formulas, it is obvious. If you once understand in which mass state neutrinos have been produced, there is no room for oscillations. But we show it in a more vivid way, just that indeed, if we see oscillations, there is no possibility. If there is no possibility to say in advance in which neutrino mass states have been produced, or vice versa. And only if the uncertainty in determination of momentums and energies of initial pi and millions is less, and just to provide the possibility to understand in which neutrino mass state is produced, only in this case neutrino oscillation condition, coherence of neutrino oscillation is valid. So this is a violation of coherence, violation of the coherence condition. No oscillations. No oscillations. This is more or less what I have in mind to finish our discussion of neutrino mixing and oscillation in vacuum. And the next our stage, the next our problem, our topic is neutrino oscillations in presence of matter. And I think that probably we shall start this discussion and then finish it next time. So, of course, we should recall an example that we have discussed, you have discussed several times. You know that when a photon is propagating in a vacuum, it moves with the speed of light, because the mass, the mass is zero, yeah? When the photon is propagating in media, the energy-momentum relation is violated. the mass become not zero. So the presence of environment violate the energy momentum relation, yeah, in the case of photon. Obviously, the same will happen with neutrinos. Due to interaction with the particles of environment, the energy momentum relation for neutrino will be violated, disturbed. And from the game we just were playing during the previous hour, you understand that this is what is very important is the wave propagation and energy momentum relation. Once this energy momentum relation is changed or influenced by the presence of environment, so it means that the oscillation neutrino pattern will be violated by the presence of matter with which neutrino propagates. So, and now I would like to just start a new part, neutrino mixing and oscillations in matter. So, for the photon, we know in vacuum the mass of the photon equals to 0, and we know that the energy equals to momentum. Yeah. Okay, that's right, like this. Yeah. In matter, the mass of the photon in matter is equal not 0, and we know that there is so the relation between the energy and momentum is changed. The same is for neutrino. The same is for neutrino. Now let's consider again two types of neutrinos: electron and mu neutrino, and also two mass states of neutrinos, nu1 and nu2, with mass 1 and mass 2. Yeah. And we would like to calculate what happens with these neutrinos and how the energy momentum relation will be changed due to interaction of neutrinos with the environment. So we have to calculate the shift of the energy of flavor neutrinos, electron and mu neutrino, due to neutrino interaction with the particles of the environment. And then we add this shift to the effective Hamiltonian of neutrino propagation. This is our goal, yeah? So we have to calculate the shift, effective shift of energy of electron and mu neutrinos in the presence of environment. Let's suppose that matter is composed of neutrons, protons, and electrons. And also, this is normal matter, yeah? All matter is composed of these particles, if it's not extreme conditions when we should account for the structure of neutron, of proton, etc. If the temperature is very high, a reasonable part of muons can appear, etc. Yeah, but this normal matter here in the Earth, in astrophysics, not in the early universe. Yeah, and also we suppose neutrality. It means that the number of electrons equals to the number of protons. This is called the electron number density. По-русски это плотность электронов. Number of electrons in the cubic centimeter. This is this particle number density. Electron number density, proton number density, neutron number density. Yeah? This is normal matter. No, it's neutral. Normal matter is neutral. Yeah? Okay. And now we can we should consider evolution of two neutrino flavor states, neutrino electron and neutrino muon, in presence of this particular matter. Normal matter composed of electrons, neutrons, and protons, and also electrically neutral matter. Yeah? So we should address to the Lagrangian of the Standard Model that describes interaction of flavor neutrinos, electron muon neutrinos, with these particular particles. Yeah? And we can classify in this Lagrangian the so-called contribution from charge current interaction and neutral current interaction. Charge current interaction is the interaction that are mediated by the charge boson, and the neutral due to neutral boson. Yeah? And we start with the charge current interactions. Well, sometimes people make charge current interaction. Yeah? Let's write the typical diagram, Feynman diagram for this process. This is neutrino, this is an electron, neutrino. This is the W boson plus here electron and electron neutrino. Yeah? Let's put the momentous of P1, here P2, P4, and P3. This is how electron neutrino interacts with electrons. Yeah? What about similar contribution for muons? What you can say? We can write the same diagram according to universality of weak interaction, but here we should put muon neutrino, muon neutrino. Okay? But in normal matter, the number of muons is 0. So it means that only this guy, only this term, only this contribution survives. For the normal matter, we just specify the matter composed of electrons, neutrons, and protons. Yeah? Okay. Muons can appear when a high temperature exists in the environment, probably somewhere in extreme conditions in the early universe, etc. Probably. Okay. This Feynman diagram from the Standard Model Lagrangian, we can write that this has the following expression for this. G is a coupling constant. There are three coupling electron, E, G prime, G. Yeah? This is one of coupling constants of the Standard Model. This electron bar left. Сейчас мы закончим, одну секундочку. 1 gamma lambda electron left P2 Then there is the propagator of the charge boson, G lambda rho, divided by P2 minus P1 squared minus the mass of W boson. And then new electron left bar, momentum P3, the sum over these indices is left per 4. So this is an expression that comes exactly from the standard model Lagrangian that describes the contribution of this diagram of interaction of electron-neutrino with electrons. So I think that we should stop here, yeah? And we'll continue next time. Yeah. Well, thank you very much.